Hi students, in this session we will discuss about the topic filter characteristics of linear systems. First we will see this topic and then we will move on the distortionless transmission. Okay, first we will go with the filter characteristics of linear system. Okay, so filter characteristics of a linear system. So for a system, generally we will consider the input as x of t and output as y of t. So for a system, the input will be x of t and output will be y of t. Okay, that is, the system is taking the input as x of t and it is processing the signal and it is producing the output as y of t. So that is, the system is processing the input signal and producing another signal as output, that is y of t. So the system therefore process the signal x of t, process. Okay, so the system is processing the signal x of t in a way that is characteristic of the system. So that depends upon the characteristic of the system, it is processing the signal. So the system processes the signal x of t in a way that is characteristic of the system. Based on the characteristic of the system, it is processing the signal. So depending on the characteristic of the system, it will process in different ways. Okay, so the system processes the signal in a way that it is characteristic of the system. Okay, here consider the spectral density function of the input signal x of t is given by x of s or x of omega. The spectral density function of the input signal x of t is given by x of s or x of omega. In the same way, the spectral density function of the output signal y of t is given by y of s or y of omega, that is in s domain and in frequency domain. Okay, now we all know that y of s will be equal to h of s into x of s, or the transfer function h of s is nothing but y of s by x of s. So y of s equal to h of s into x of s. We all know this. In the frequency domain, the y of omega equal to h of omega into x of omega. Okay, this h of omega is nothing but a transfer function in frequency domain. This is the transfer function in s domain. Now, the system, what the system will do? The system modifies the spectral density function of the input. Here, the system modifies the spectral density of the input with the help of the transfer function h of s. That is, here the x of s is the spectral density function. So the system is modifying that spectral density function x of s with the help of h of s, and it is producing the spectral density function as y of s at the output. Okay, the system modifies the spectral density function of the input. That is, the system acts as a kind of filter. Here the system acts as a kind of filter for various frequency components. Simply, here the system is modifying the spectral density function of the input. Okay, so x of s is modifying to y of s. It is modifying. That is, the system acts as a kind of filter. Here the system acts as a kind of filter for various frequency components. So for this range of frequency component, it acts as one filter, and this range of frequency components it acts as another filter. So here the system acts as a kind of filter for various frequency components. That is, some of the frequency components are boosted. That means in the whole frequency component range, some of the frequency components are boosted in strength. Boosted in strength means the signal strength is amplified. They are amplified. So some of the frequency components are boosted in strength. That is, some of the frequency components are amplified, and some of the frequency components are weakened in strength. Okay, that is reduced in strength, nothing but attenuated. So some are amplified, some are attenuated, and some of the frequency components are unaffected. Some may be unaffected. So it will not go with some frequency component, but for some frequency components they are amplified, and for some frequency components they will be attenuated or reduced. That is, here each frequency component suffers a different amount of phase shift. So this is with respect to magnitude. Now we go with respect to phase. That is, each frequency component suffers a different amount of phase shift. That is, each frequency component will undergo a different amount of phase shift. Each frequency component will undergo a different amount of phase shift. That is, h of omega acts as a spectral shaping function, because here the spectral density function x of s is modifying by using h of s, or x of omega is modifying using h of omega. That is, h of omega acts as a spectral shaping function. Simply, it acts as a spectral shaping function. Which frequency components you have to pass, which to stop, which to amplify, which to attenuate. So h of omega acts as a spectral shaping function. Now, the LTA system acts as a filter. So the LTA system will act as a filter here, and the filter is basically a frequency selective network. Frequency selective network. Simply here, based on all this, you can conclude that the LTA system will act as a filter. Okay, it is changing the spectral density functions. Okay, so some may be amplified, some may be attenuated, some may remain unchanged, and there's each frequency component has a phase shift. Here the h of omega acts as a spectral shaping function. So simply the LTA system acts as a filter. Filter is nothing but a frequency selective network. The filter is basically a frequency selective network. So it will select a range of frequencies. Frequency selective network. That is nothing but filter. So here each filter will select a range of frequencies and allow those, or they reject those. So they will select a frequency. So basically a filter is a frequency selective network. Now simply here the LTA system acts as a filter, and this filter is nothing but a frequency selective network. Okay, it will select some frequencies. Now see how it will select. Based on this, how the filters are classified, how many filters we have, we will see all this here. Some LTA systems allow the transmission of, here some LTA systems, I said LTA system acts as a filter. So some LTA system allow the transmission of, some LTA systems allow the transmission of only low frequency components. They will allow only the low frequency component and stop all high frequency components. Some LTA systems will allow the transmission of, that means they will allow low frequency components to pass through them, and they will stop all the high frequency components. That means high frequency component does not pass through that LTA system. They are called as low pass filter because they allow only low frequency components. They allow low frequency components, hence they are called as low pass filters, and simply are LPF, low pass filter. Low pass filters LPFS. Okay, and some LTA systems allow the transmission of, and some other LTA systems allow the transmission of only high frequency components, and stop all the low frequency components. It will allow only the high frequency component and stops all the low frequency. That is, through some systems only high frequency components will pass and low frequency component does not pass. They are called as high pass filters. High pass filters, nothing but they will allow only the high frequency component and stop all low frequency components. And next one, and some other LTA systems allow the transmission of only a particular band of frequencies, only a particular band from this frequency to this frequency. In that range only they will allow and stop all other frequency components, and all other remaining components they will stop. They are called as band pass filters. Simply BPF, band pass filters, because they are allowing only a particular band of frequencies, particular band, some frequency omega 1 to omega 2, some particular band of frequencies. Hence they are called as band pass filters, and they will stop all other frequencies except that band of frequencies. Okay, so the band of frequency components will go through the system and the remaining will stop by the system. So as they are allowing only a particular band of frequency components, they are called as band pass filters. Okay, and some LTA systems reject only a particular band of frequencies, and allow all other frequency components. Say if there is omega 1 and omega 2 in this range, they will reject all the frequencies and allow all remaining frequencies. That is, some LTA systems reject only a particular band of frequencies, and allow all the frequency components. They are called as band rejection filters, BRF, band rejection filters. Okay, band reject. That means those band of frequency components are rejected by those filters or those LTA systems, and they are called as band rejection filters. So here we have four types: LPF, low pass filters, which allow all the low frequency components; high pass filter, HPF, which allow all the high pass frequency components; and BPF, which allow only the band of frequencies; and BRF, which reject a particular band of frequencies and allow all other frequency components. So these are how the LTA systems are classified as LPS filters, low pass filters, high pass filters, band pass filters, and band rejection filters based on their functioning. Okay, now the last, the band of frequency that is allowed by the filter, the band of frequency or the band of frequencies that are allowed by the filter are called pass band, because the filter is allowing the band of frequencies. Inside this all are allowing. So that is nothing but pass band. So the band of frequencies that is allowed by the filter is nothing but is called pass band. The same way, the band of frequency that is severely attenuated is called stop band. That is not passing through that. The band of frequencies that is severely attenuated, stopped, not passed through the filter is nothing but the stop band. Okay, they are stopped by the filter. So in the band of frequency that is allowed by the filter is called the pass band, and the band of frequency that is severely attenuated or stopped by the filter is called stop band. That is, it will not pass through the filter, otherwise will not pass through the LTI system. So this is regarding the filter characteristics of linear systems. First, I had gone for the filter characteristic, that is, I explained about what is a system, how the system will function, and spectral density function, and finally I concluded that LTI system acts as a filter and what is the purpose of a filter, and I gone for the different types of filters of these LTI systems, and what is finally I concluded with what is a pass band and what is a stop band. This is the complete explanation about the filter characteristics of linear systems. Okay, now we will go for the distortionless transmission. Now we move on to the topic distortionless transmission through a system. Distortionless, that means while transmitting signal through a system, it will not be distorted. So we will see that type of transmission. So distortionless transmission through a system. First, I will explain what the distortion is. The change of shape of the signal when it is transmitted through a system. If a signal is transmitted through a system, at the output, if there is any change of the shape of the signal with respect to the input, then we call that as a distortion. That is the change of the shape of the signal. The change of the shape of the signal when it is transmitted through a system is called distortion. Consider a system. If you apply some input signal x of t, okay, the system will process the signal and it produces output y of t. So if the y of t shape is different from the x of t, then I can say that signal is distorted. That is nothing but the distortion. Okay, the change of shape of the signal when it is transmitted through a system is called distortion. When we transmit a signal through a system, if it is distorted, if the shape of the signal is changed at the output, then we call that as a distortion. Okay, now the transmission is distortionless. The transmission will be distortionless if the output is exact replica of input signal. So the output of the system is exact replica of the input signal, then we can say there is no distortion. That is distortionless transmission. So in distortionless transmission, the output is exact replica of the input signal. Here we have to remember some constraint. That is, the replica may have different magnitude and different time delay. Important. So in that replica, that is, the output is exact replica of the input I said. So in that replica, the replica may have different magnitude and different time delay. So the magnitude of the signal may change and there is a delay in the time for the signal, but the shape does not alter. Here the shape is important. The shape has not to alter. There may be change in magnitude, that is, the signal magnitude may increase, or there may be a time delay. That means if it has to start at 0 second, it may start at 5 seconds. If it is started at 0, it may start at some t after t seconds. So there may be a delay, time delay, and there may be a amplification in magnitude. That is, the magnitude may be different and there is a different time delay. So that we can't consider, okay, as distortion. That is, in the output signal we may have different magnitude and different time delay. That we can't consider as a distortion. Here the constant change in magnitude and a constant time delay are not considered as distortion. Only the shape of the signal is important. Only the shape of the signal. Only if the shape of the signal changes, then we consider that as a distortion. If the magnitude, there is a constant change in the magnitude, we won't consider that as a distortion. Or if there is a constant time delay also, we won't consider that as a distortion. So mathematically, we can write the output y of t equal to k into, here mathematically we can write the output y of t equal to k, where k is a constant, some constant into x of t minus td. Here k is a constant with which the magnitude will be increased. Okay, so this k will be the a different magnitude. This is for amplification or attenuation of the magnitude. Okay, this is k value, and this x of t minus td, x of t minus td is, there is a delay of this td. So td is the delay time. So here the output magnitude is either increased or attenuated with the constant k, and it is delayed by td. Even though we can say the transmission is distortionless transmission, because the shape is same, only the change is with respect to magnitude and with respect to the time delay. Hence we can say that as an distortionless transmission. So for the distortionless transmission, mathematically we can write the output equation as y of t equal to k into x of t minus td. So for distortionless transmission, we can write the output equation mathematically as y of t equal to k into x of t minus td. Here k is a constant, that is change in amplitude. What the amount of change that is occurred in the amplitude, either attenuation or amplification. Okay, and td is the time delay. Here td is the time delay. So for this theoretical explanation, I will go for the diagrammatic explanation. See the diagram. So distortionless system. So this is a distortionless system. For this, consider an input like this. So this is the input signal. Okay, this is the input signal. Okay, so on a t, and this is x of t, and this amplitude is 1. This is given to a system with impulse response h of t, and it is producing an output like this. See here, there is a delay. Okay, so instead of starting at 0, it is starting at some td. Okay, see the shape is same, but here the amplitude is increased, that is the magnitude is increased. Here it is 1, it is increased by k times, hence I written as k. And instead of starting at 0, it is starting at td, that is the time delay of td. Okay, time delay of td. See, the shape is same. Hence this is the equation for, on x-axis it is t, on y-axis the output diagrammatic representation of the output y of t equal to k into x of t minus td. Here what happens? The signal amplitude is increased to k times. So increased to k times. And instead of starting at 0, it is started at td. That is, there is a delay of td. Time delay is td. Hence I represent this waveform equation as y of t equal to k into x of t minus td. Here we can say there is no distortion because the shape is same. There is no change in the shape. All the change is in with respect to magnitude and time delay occurs. So this is nothing but an example for distortionless transmission. So this is a distortionless transmission system. We can call this as a distortionless transmission system. Okay. Now see, let us consider, you can take the Fourier transform on both sides, taking the Fourier transforms on both sides of equation y of t equal to k into x of t minus td. Okay, so take the Fourier transform. So consider this equation, that is equation for y of t equal to k into x of t minus td. So take Fourier transform on both sides for this equation and use the time shifting property. Here use the time shifting property. So Fourier transform, if you consider the Fourier transform, y of t will become as capital Y of omega and x of t will become as x of omega, but here it is x of t minus td. There is time shifting. Whenever there is a shift in the time, then we have to multiply with e power minus j omega td, that is e power minus j omega t naught in the frequency domain. So that is the property of time shifting. So here they applied the Fourier transform for this and they used the time shifting property. Then the equation converted into y of t will become as y of omega, that will be equal to k as constant k, and x of t minus td, that is time shifting property. So for that the Fourier transform will be equal to, x of t is having Fourier transform x of omega and x of t minus td will have a Fourier transform e power minus j omega td into x of omega. So for this equation, if apply the Fourier transform and use the time shifting property, we will get y of omega equal to k into e power minus j omega td into x of omega. For distortionless transmission, the transfer function h of omega will be given as H of omega will be equal to y of omega by x of omega. So bring x of omega this side, y of omega by x of omega. That will be equal to k into e power minus j omega td. So for the distortionless transmission, the transfer function of the system should be equal to k into e power minus j omega td. Now, if we want the impulse response of the system, what we have to do? I have to go for the inverse Fourier transform. Now take the inverse Fourier transform. So by taking the inverse Fourier transform of this one, I will get the impulse response of the system h of t equal to k into, so inverse Fourier transform, h of omega inverse Fourier transform will give h of t, and inverse Fourier transform of this one. See, so the Fourier transform of del of t minus td will be equal to e power minus j omega td. We all know the Fourier transform of del of t minus td. Del of t minus td will be equal to e power minus j omega td. Hence, inverse Fourier transform of e power minus j omega td will be equal to del of t minus td. So h of omega h of t, and for this the inverse Fourier transform is del of t minus td. So h of t equal to k into del of t minus td. So this can be obtained by applying the inverse Fourier transform to this h of omega. Okay. Now here, that is the magnitude of the transfer function. That is mod of h of omega equal to, so mod of h of omega, the magnitude of this one will be equal to k. That is the magnitude of the transfer function h of omega will be equal to the value k for all values of omega. For all values of omega, the magnitude of the transfer function h of omega will be equal to k. And the phase shift, go for the phase shift. Theta omega, theta of omega or angle of h of omega will be equal to minus omega td, because magnitude into e power j theta. So the representation will be equal to mod of that value, that is mod of the signal, that is magnitude into e power j theta. Okay, the theta is the phase angle. So here, if you go for the mod, that is the magnitude of the transfer function h of omega will be equal to k. Okay, for all values of omega. And the phase shift theta of omega, nothing but angle of h of omega. So angle of h of omega will be equal to this one, minus omega td, minus omega td. So there, first I gone for the Fourier transforms, and using the time shifting property, I find the equation of output signal in the frequency domain. Then I find the transfer function for the distortionless transmission, and using the inverse Fourier transform, I got the impulse response. Okay, here I gone for the magnitude of the transfer function and phase shift of that transfer function. Okay, that is magnitude response and phase response. I can draw using these values. I can get the magnitude response as well as phase response. I will show you. Okay, see the magnitude and phase characteristics of a distortionless transmission system. Magnitude and phase characteristics of a distortionless transmission system. See here, this is k, that is constant for all values of omega. So consider this as omega. For all values of omega, for all values of omega, we are getting the magnitude as k. Hence, I drawn a straight line. I drawn a straight line. So it is of infinite bandwidth, so straight line. For all values of omega, right, from minus infinity to plus infinity, the value of mod of h of omega. So I drawn the graph for omega and mod of h of omega. The mod of h of omega is k for all values of omega. So for all values of omega, it is k. Now we go for the phase response. This is the magnitude response. Now I go the phase response. Phase response is a linear phase shift. Linear phase shift. Hence I draw on a line, linear straight line. Okay. Hence I go on for a linear. Okay. And this theta of omega equal to minus omega td. Okay, minus omega td, the linear phase shift. So here we get the linear phase shift. So you go for the magnitude and phase characteristics of a distortionless transmission using these two equations. One is h of omega equal to k, this one, and theta of omega, angle of h of omega equal to minus omega td. So theta of omega, or the angle of h of omega equal to minus omega td. For this I will get this line, and for this I will get this line. Okay, this is for k value. So there is the magnitude and phase characteristics of a distortionless transmission. Now see, for distortionless transmission, the magnitude of the transfer function, the mod of h of omega is constant. So that is all the frequency components will undergo a constant amplitude or attenuation. All the frequency components should undergo a constant amplitude or attenuation. That is, the system bandwidth is infinite. The system bandwidth is infinite, constant. The amplitude is raised constantly or attenuated constantly. That is, the system bandwidth is infinite, and the phase spectrum should be proportional to the frequency, and the phase spectrum, and the phase spectrum should be proportional to the frequency. So here the phase spectrum is proportional to frequency. The system bandwidth is infinite. But in practice, in general practice, okay, for practical purpose, no system can have infinite bandwidth. No system can have infinite bandwidth. Practically, there is no system with infinite bandwidth. There is limitations in practical considerations, and hence distortionless conditions are never met exactly. So this distortionless conditions will not met exactly. Why? Because for the distortionless transmission, the system bandwidth is infinity, but practically there is no system with infinite bandwidth. Hence, the distortionless condition does not met exactly. Okay. Now, for this distortionless transmission, the system must be of linear phase. The system must be of linear phase because the amplitude magnitude is constant, but the phase will vary linearly. Hence, for distortionless transmission, the system must be of linear phase. That will be surely of linear phase. So, for linear phase systems, that is, the phase is varying linearly. For linear phase systems, the impulse response, that is h of t, is symmetrical about t equal to td. Whenever the t value is equal to td, then it will be symmetrical. The impulse response is symmetrical about t equal to td. So this is for your work. You have to prove that for linear phase systems, the impulse response will be symmetrical about the t equal to td. So you have to prove that. So simply that will be proven by considering the equation h of omega. So go for h of omega equal to k into e power minus j omega td, or you can write h of omega equal to mod of h of omega, because the k value is nothing but mod of h of omega. So in place of we can write mod of h of omega into e power minus j omega td, or we can use this one, okay, and go for the inverse Fourier transform and prove that impulse response h of t is symmetrical about t equal to td. Simply you have to find out the value of h of t, because you know the h of omega. From that you can find the h of td. Okay, so there you have to prove that is symmetrical. For if you know the h of t, then you can go for the substitutions and prove that impulse response is symmetrical about t equal to td. Simple. This is how you have to do the. First you have to consider this equation h of omega, and you have to find out the inverse Fourier transform h of t, and then you have to prove the impulse response is symmetrical about t equal to td. So this is for your practice. I hope you will do that at your home. That is for your work. So this is completely about the distortionless transmission through a system. First I explained what a distortion is, okay, and then how the signal will be transmitted without distortion, and I have given the mathematical equation for the output signal, okay, and I have given a diagrammatic representation of distortionless systems, and I gone for the transfer function for this distortionless transmission, and then I gone for the magnitude and phase characteristics of the distortion transmission. Finally, I gone for said that is this distortionless transmission systems will have an infinite bandwidth, but practically it is not possible, okay, hence these conditions will not met exactly, okay. And finally I gone from this you can say that the distortionless transmission system must be of linear phase. So for linear phase systems, the impulse response is symmetrical about t equal to td. At t equal to td, it will be symmetrical. So I had given this for your work. I hope you will prove that, okay, you will do that. So this is completely regarding the distortionless transmission through a system, okay. With this I am finishing today's class. Thank you one and all.